Welcome back to module 7. We are discussing non-radiative transition due to non-adiabatic coupling. We haven't shown the exact form of the coupling yet, but we have shown that this is going to be a constant coupling, time independent coupling rather, and that's why we have considered a constant interaction potential, which is coupling two states, let's say discrete state and a continuum state. And we have shown the integral differential form of the TDSE, which we get in the derivation of quantum dissipative dynamics. And so far what we have shown is that this is the form we get, and we have to get a solution. We have to reduce this equation. This equation looks very complicated, but if we use a few more assumptions, this equation can be reduced to a very simple form. And our target so far is to find out how this CNT population in the initial state is varying, and it should vary like an exponential decay. So, we will move forward as in the integral differential form we had this integration. So, we will look at the first time integration part. We'll go part by part. So, in the integral differential equation we had this time integration, and then this is the time integral part, and then this is the state integral part. So, two integrals will look at it separately. So, first we will look at the time integral part. If we look at the time integral part, we see that this is an interesting and very familiar form. We have used a pulse. We have introduced in the module 1, we have introduced a pulse. The pulse looks like this, an optical pulse particularly. And then also we have introduced wave packet, is the same concept, similar concept. Wave packet is localized particle wave in space, and the optical pulse is the localized electromagnetic wave in time. But both having similar idea, it has an envelope function and a very fast varying carrier wave, which is represented by cos omega naught t, but generally trigonometric functions are difficult to deal with. That is why we have always represented by e to the power I omega naught t. That is the usual representation in the time domain, the pulse. And so finally the electric field is represented as AT multiplied by e to the power I omega naught t. That is the we have represented. This is the slowly varying component, this is the fast varying component, and the concept of slowly varying and fast varying, we have already demonstrated those concepts in module 1. So, it will be much easier to understand now. And because it is a very slowly varying component, just check just note the similarity between this mathematical function and this integrand here we have. This is also just like a slowly varying component, and then e to the power something is the fast varying component. And this similarity shows that we will be able to further reduce following the slowly varying envelope approximation. So, we will consider a slowly varying envelope slowly varying coefficient approximation. In this approximation we are saying that CNT dash, this is time varying part, CNT dash is very slowly varying as compared to this part. And if it is slowly varying, then one can say that CNT dash is approximately equal to CNT. And if it is so, then one can take this CNT dash e to the power I En minus Em t minus t dash by h cut dt dash. One can take this out of the integration and we have only e to the power I en minus em t minus t dash by h cut dt dash. We have this, and this can be taken out within this approximation that CNT is very slowly varying. That's why within this integration it's slowly varying and it's adapting the final value. So it is almost constant within this integration time interval, we can say, and the constant value is nothing but the CNT value. That's the way we are saying. So and a slowly varying envelope approximation, one can say that because you see, if you look at this variation, the fast variation. So if I am integrating between, let's say, this time interval or this time interval, one can see that how much variation I have in the fast varying component, whereas slowly varying component didn't change much. We'll say that this is almost similar, and that's the approximation we are making. So within this approximation one can take it out, and after taking it out one can assume that t minus t dash equals tau, new variable definition I am giving, and in that case dt dash minus dt dash is going to be d tau. So this integral part can be written as CNT, then this is going to be then limit is going to be then t to 0, and there will be minus sign here because of this dt dash, and then e to the power I en minus em tau d tau divided by h cut. And so which is nothing but CNT 0 to t as a to b fx dx equals nothing but b to a. If we change the limit, it becomes a negative sign. So something like we are using this a concept here to change the limit like this, and then I get e to the power I en minus em tau divided by h cut d tau. That's the integration we have, and this integration can be evaluated if I consider that t tends to infinite, which means that the integral, the limit of the integral is considered to be infinite, which means we are looking at the long time response. If we use the long time response, then this integral becomes infinite, and the moment I take it infinite, then I have one definition of Dirac delta function. Dirac delta function has many definitions. In this module we have shown Dirac delta function has a definition in terms of cardinal sign function. Now here the definition which I am going to give right now, that definition we have used already in the translational motion, quantum dynamics of translational motion. That is the 2 pi delta k minus k dash equals minus infinity to plus infinity e to the power I kx e to the power minus I k dash x dx, which is nothing but 0 to infinity. If we consider 0 to infinity, if it is a symmetric function, then I can write down like this way. Within the 0 to infinity, I can write down the same equation as twice of this dx. So this is the definition of Dirac delta function, and this definition we can use to so this is nothing but pi delta k minus k dash. And one can use this Dirac delta function definition to reduce this equation, because as we are taking long time response, this t, this is going to be infinity, and for long time response this part is going to be now Cnt, then pi, then delta function of En minus Em divided by h cut. And because we have previously used delta Ax equals delta x by A, that's why we can write down this as Cnt pi h cut delta En minus Em. So the entire within the approximations which we have made, slowly varying coefficient approximation, as well as using this Dirac delta function, and also long time response if we consider, then this entire time integral becomes like this. On the other hand, we have this integration, the special integration like this, where we are integrating over all states, and we have to remember that I can have the same energy, at the same energy level I can have many states available. So this is M1, this is M2 states, this is M3 states, this is M4 state, like this. So this integration is over all states, not energy states. So this is over all states. What I need to do is that, because here I have found an expression in terms of energy level. This is En and Em are energy levels. So this is the energy level for this. This is another energy level M dash. This is another energy level M double dash. So for a same energy level I may have different states, and this integration is over all states. All we need to do is that I have to convert this integration to over energy levels. So this is going to be then over energy levels. And in order to do that, what I will do, I will consider the density of states. So if we assume that rho Em is the density of states, which means that rho Em dEm gives me total states in dEm range. So one can write down, and this is the total states in dm range, and probability of transition to each state, each energy level is given by Em. So in that case I'll be able to write down 0 to infinity dm m h dash n this integration is nothing but 0 to infinity dem rho em Em H dash n square. So this part, this integration we are doing in terms of states, and this integration we are doing in terms of energy levels. We are just changing the representation, and if we do that, then things will be very easy to deal with, because now I'll do one thing. I will just consider this part to be a function of some energy. So I'll be able to write down as dm k some function of em. So this k em is a function of energy levels, which is given by rho em, density of states at that state, at that point, at that energy level, and the probability of transition to that energy level. This is just a function of energy. So now we'll go back. These two representations will be used, and we see that this portion can be written as this delta function multiplied by these parts, and this integration can be converted to over the states, over the energy levels. So if we do that, then we get following. We get dCN T dt equals minus, I have now CNT by h cut square, then I have h cut pi, and then I have this integration. Integration is going to be 0 to infinity DEM KEM and delta EM minus EN. That's the integration we get. And this part is a familiar integration because we use similar kind of integration in the translational motion when we have described translational motion in module 3. What we have used there, if I have a, let's say, smooth function fx, if I have a smooth function fx and I'm integrating that smooth, multiplying this smooth function with a delta function x minus x naught and integrating it over space, then the value of the integration would be the value of the smooth function at the position of the delta function, and at the position of the delta function is x naught. So if the integration limit is considered to be 0 to infinity, then that is going to be 2 of this fx delta x minus x naught dx is going to be fx naught. So finally this is going to be half of fx naught. This is something which is a property of the delta function. If a smooth function is multiplied by a delta function, then the value of the integration is going to be the value of the function at the position of the delta function, where the delta function exists, and delta function exists when x equals x naught. So that concept can be used here. We will assume that the KEM is a smooth function which has been multiplied by delta function. That's why this value of this function is going to be, then this is going to be now CNT divided by h cut pi, and then is going to be half of this function at the delta function value, which is n. At this value I have to find out this function's value. So, if we assume that this entire k em equals en half pi by 2 h cut, this entire thing is nothing but tau, let us say. We assume that is tau. So, in that case I will be able to write down, simplify this equation as Cn t divided by dt equals minus tau Cnt. Simple equations we have got, and this equation can be integrated with the assumptions that Cn 0 was 1. So, if we do that, then I will be able to get this integration to be Cnt1. So, integration would be done from 0 to t1 time, then I will be able to get this to be to the power minus tau t1 or Cnt square of the absolute value of the Cnt is going to be to the power minus 2 tau t1. So, this is the expression which is very useful, because now it is showing that the population in the initial state, that is the initial state I started with n, population in the initial state is decaying as a function of interaction time exponentially. So, now I have been able to reproduce this exponential decay law, that is the quantum dissipative dynamics, whereas a linear decay law was predicted by Fermi's golden rule. So, which means that Fermi's golden rule is applicable for short time decay. It cannot represent the long time decay. Long time behavior can be explained through this quantum dissipative dynamics, where we are using integral differential form of the TDAC. So, we have come to the conclusion end of this module, where we have discussed non-radiative transition from one discrete state to another discrete state, and from one discrete state to a continuum of states. We have seen that Fermi's golden rule for the non-radiative transition is controlling the transition probability for the short time of the process. If I have to represent it in the long term process, then I have to use this integral differential form of the TDAC. So, we will stop here, and we will continue the discussion of time dependent quantum chemistry in the next module.